All right, so it is my pleasure to talk to you about NASA's Heliophysics Division, which is everything under the sun. We like our acronyms, we like our single words. So we came up with heliophysics to really mean everything that the sun controls, everything that it looks after, and everything that it impacts. So it impacts all the way from the very, very close into the sun, all the way out to the very edge of our solar system, as it actually shapes the very cavity that our solar system orbits around the Milky Way in. And so we have a fleet of spacecraft in the Heliophysics Division that actually study that. We have a lot of spacecraft that are very close to the Earth. They're looking at the ionosphere thermosphere system. We move out, we cover the magnetosphere. As we move further outside, we can see our solar observatories that watch the sun 24/7. You can see SOHO, WIND, and ACE that are monitoring everything that is coming from the sun in the solar wind. And then if we move a little further out, as we move away from Earth and we pass by the planet the orbit of Venus and Mercury, then you'll see the very plucky Parker Solar Probe that is orbiting the sun in very large petal orbits, launched last year and already bringing great science results. We've seen papers in Nature and incredible science results presented here today. And then if we go even further out, all the way out beyond Pluto to the very edge of our heliosphere, our Voyager spacecraft that have been on orbit or in space for now 42 years, still sending back vital information to us about our very edge of space, and in fact now interstellar space, having crossed for the very first time out of the sort of influence of our solar wind. But very close to home, we love our sun. It not only is it the sun that we have to live with, and it has big impacts on us, but it's actually a star. It's the only star right now that we can actually go and visit. And so we go in and we study all of the wonderful things that our star does. We've looked at the sun in just about every different wavelength possible. We've been in as close as the planet Mercury, but not until last year when we launched Parker Solar Probe were we able to really go into this magic region, this region where all of the action happens. When you look at the sun invisible, it looks like a fairly uniform yellow disk. You may see a couple of small dark spots on it that we call sunspots. But when you look at the sun in any other wavelength, you see that it's an incredibly, incredibly active star, regularly having events that throw billions of tons of this coronal material out into space, often actually impacting our planet. So here is Parker Solar Probe daring and flying very, very close to the sun. Flying through the sun's corona. The reason we needed to do this is that there are mysteries in the corona that we have not yet been able to explain. One is that hazy atmosphere that you see during a total solar eclipse is about 300 times hotter than the surface of the sun, and that just doesn't really make sense. Also, where we see this incredible heating, we also see big acceleration. And so the plasma that would normally be constrained on the magnetic field lines and held close to the sun, it's a big giant star, it's got a big gravitational pull, but despite that, this material can actually be accelerated and move away from the sun, bathing all of the planets and indeed shaping our heliosphere. So we've had wonderful results from Parker Solar Probe here at the meeting. This is sort of a view of what Parker Solar Probe is seeing during the first orbit. And so you can see how big the sun actually looks. That gives you an idea of how close Parker Solar Probe is to the sun. In the current configuration, she's about 15.8 million miles away from the sun. We will do a second Venus flyby in December 26th of this year, and she will go to a smaller configuration, and then her closest approach will be about 12 million miles away from the surface of the sun. So here's data from the Whisper camera. This is one of the instruments aboard Parker Solar Probe. This imager it's not a traditional solar imager. It doesn't take pictures of the sun, but it's taking pictures of the solar wind and all of the structures that the spacecraft is about to fly through. It's extremely important for us because we're now in a region where we've never been before, and so we're having these incredible data, these new results, and it's really helping to be able to explain what we're seeing because we can look at the structures and the type of solar wind that we're flying through. One of the big results that was published in Nature last week was actually what we're calling switchbacks. And so if you look at the magnetic field here, this is a magnetic field line moving away from the sun. We would expect that magnetic field line to be straight, but actually what we see are these sort of S-shaped curves that we're calling switchbacks. And if you think of a magnetic field line a bit like a rubber rope, it's extremely hard to get it to bend back and do this strange configuration. So there is some kind of wave structure that is going on in the corona that is causing these S-shapes to occur. And as those S-shapes relax, they're letting an awful lot of energy out into the solar wind. And so we think this is definitely one of the mechanisms that we're now seeing that is causing this heating and acceleration of the solar wind. So even on the very first orbit of Parker Solar Probe, we're already getting results for our overarching questions of why is that corona so hot and why is the solar wind continually accelerated. So when the solar wind, so when the sun is very active, it will throw off these very large events. Also, as I mentioned, continually flowing, not just when we see these large events, but this solar wind is continually flowing. So it's continually sending these huge streams of particles out into interstellar space. So as it leaves the sun, these particles will come, and first of all, they wrap around any of the planets that are between the sun and us. And so I think you'll see the first thing is it goes past the planet Mercury, and then onto the planet Venus, and then it's kind of a strange feeling. I feel like it's coming up to get me from behind. So it's going to go around the planet Venus. Venus doesn't have a particularly strong magnetic field, so it doesn't have a huge impact when it gets to Venus. But you'll see the difference when those particles get to Earth. Earth has a very strong magnetic field, and so that our magnetic field will actually repel a lot of those particles. It guides them around our magnetic environment, our magnetosphere, keeping most of that really dangerous radiation out. And so you can see the way they get sort of channeled around. Of course, some of the energy gets in just because we keep the dangerous particles out. We can actually get a lot of energy from the solar wind coming in and causing big configurations, big changes in our magnetic field. And those changes in the magnetic field actually give rise to the very beautiful northern and southern lights, I should say. And so as all of this energy comes into the magnetosphere, as the magnetosphere kind of relaxes, these particles come shooting down the field lines. They impact the ionosphere, and they impact the gases that we find in the ionosphere. So mostly that is oxygen and nitrogen, and they cause it to glow. So the colors that you see in the aurora are a fingerprint of what gas is actually glowing. So where you see green, that is an oxygen line. If you see blue or red, it is typically nitrogen. Red can also be oxygen too. But this is a nice shot. This is actually the aurora australis as the space station goes over the southern hemisphere, taking beautiful images of the aurora and also some air glow. So whenever we see big events, not only do we see the aurora, which has definite impacts for power grids, but we can also see our radiation belts. So the Earth is encircled by two belts of very, very intense radiation. When we have these really big storms, these belts can pump up both in energy and also in size, which means that spacecraft that are not designed and do not expect to be in the radiation belts can suddenly find themselves engulfed by these huge, huge radiation storms. We had the Van Allen probes that recently we had to say goodbye to our Van Allen probes because they ran out of fuel. But we've had 7 years of incredible data from those two spacecraft that have lived and worked in this region of incredible dangerous radiation. And so that's another, so we have the aurora, we also have the radiation belts, and then if we come down just a little bit further, we also see impacts in the ionosphere system. So where you would expect radio waves to kind of bounce off, or even travel through as we use our GPS signals, we see a lot of these storms that cause kind of bubbles in that region, which can stop the radio signals passing through them. And so we see every single piece of technology almost that you can imagine is clearly impacted by space weather. And so it's impacted by the solar wind and its effect on our planet. And so, of course, we worry about our technology, we worry about our spacecraft, we worry about the space station. We have passenger planes that fly across the polar routes. They can be affected when you get large amounts of radiation coming in. It can also stop communication for the polar routes, for the ships as they're going across there. But most importantly for us here at NASA, it can cause problems for our astronauts' safety. And so as we stand ready to support the Artemis program, the number one thing, of course, for us is to protect our astronauts. And the way we do that is by making these measurements with the heliophysics fleet to really understand what is happening with the solar wind and how that is going to impact our astronauts. Particularly with Artemis, we're not just going to have very short excursions up to the moon and back, but we're getting ready to do extended presence in space. And so we'll be out in the pristine solar wind, and so it makes our job in heliophysics just that bit more important and a bit more challenging, as we now have to be able to predict what is going to come from the sun and impact our astronauts. And then the final thing, of course, we do in heliophysics, not only do we worry about everything that happens here at Earth, we worry about everything that happens throughout the entire solar system. The solar wind bathes all of the planets. It's still there at Pluto. It continues beyond and further, and then at the it sort of runs out of steam, if you like. It slows down and it meets interstellar space. And there is a boundary between the solar wind and interstellar space that is continually moving, and it kind of breathes with the solar system. And so at solar maximum, the boundary is further away. At solar minimum, it kind of breathes in. And so we have our very brave Voyager spacecraft that have actually left the heliosphere. They are out in interstellar space. We also have the IBEX mission, which is taking images of the particles that are out in this boundary region. And we're also getting ready in a couple of years to launch a follow-on mission called IMAP that will really do a great job of doing sort of high-resolution maps of that outer boundary of space. And so I will leave you with my heliophysics logo. It is a great time to be a heliophysicist. We have made an awful lot of new selections. We're bringing a lot of new missions into our fleet. And we are really enjoying the tremendous results, the tremendous data that we're getting. Of course, Parker Solar Probe with all the new data. We also this year launched ICON, which is a mission that is looking at kind of the interplay with terrestrial weather, so storms and hurricanes and tornadoes from below, and how they actually impact with the space weather coming in from above. There's a very fragile region where these two systems are actually working together. So it's a really nice interaction for us with Earth science, and that's yet another new mission that we have. And so all of the data that we take in heliophysics is really driven by the solar wind, and therefore we're very excited to support the Artemis mission. And as we lean forward and we go forward to the moon, to the Mars and beyond, the Heliophysics Division stands ready to support the mission. Thank you very much.